Okay, let's just dive right in. Welcome to this explainer. Today, we're going on a pretty fascinating journey into the actual mechanics of understanding itself. I want you to think about the last time you tried to learn something completely new, something really complicated. It kind of feels like hitting a brick wall at first, right? Well, today, we're going to look at exactly how we, as humans, break down that complex information to truly learn it. And then we're going to cross the frontier to see how artificial intelligence processes the exact same world. As you'll see, there are some pretty incredible parallels between the human mind and the machine. Let's get into it. I want to kick things off with this fantastic quote from the philosopher Mortimer Adler. He essentially pointed out that if you say, you know what you think, but you just can't quite express it, well, you probably don't actually know what you think. It really hits the nail on the head regarding a fundamental truth about human cognition. True understanding absolutely requires the ability to express complex ideas simply. Basically, if you're hiding behind a wall of jargon, you haven't mastered the concept yet. So that brings us to a massive practical question. How do we actually do this? How do we take a tangled, complex mess of information, untangle the whole shebang, and truly understand it? To figure that out, we have to look at the very mechanics of how we explain things, both to ourselves and to the people around us. Actually, let's look at the grammar of the word itself for a second. According to the English Language and Usage Stack Exchange, the verb explain is what grammarians call monotransitive. Now, don't let that term scare you off. All it means is that the verb requires a direct object. You can't just explain someone, right? You have to explain something to someone. The very grammar of the word forces our focus squarely onto the core concept, the actual object that we're trying to demystify. Now, this exact idea was turned into a completely bulletproof system by the brilliant Nobel laureate Richard Feynman. It's known as the Feynman technique, and it's this beautifully simple four-step method. First, you map out everything you know about a topic on a blank page. Second, you try to teach it to a 12-year-old. And hey, if you've ever spent time with a preteen, you know for sure that requires a lot of patience. Third, when you inevitably stumble, you go back to review and refine your knowledge. And finally, you test yourself and archive that simplified explanation. So why is this so incredibly effective? Well, it's not just a neat little trick. It is deeply grounded in cognitive science. By forcing yourself to explain something out loud, you engage in active recall, which is basically like a mental workout, pulling information actively from your brain. You also use chunking to break massive ideas down so they don't totally overwhelm your working memory. And honestly, most importantly, it forces metacognition. You literally start thinking about your own thinking, and that is truly the only way to spot your own blind spots. And how exactly do you fill those gaps when you're trying to teach that imaginary 12-year-old? You use analogies. The coding educators over at Academy point out that the ultimate tool for teaching is bridging the unknown with the familiar. For example, if you want to explain variables in programming, you definitely don't start with memory allocation. You say, hey, think of variables like labeled boxes where you store your items. You start with the big picture and you bridge the gap using the real world. All right, so that's us. That's how the human brain breaks down complexity. But how does a machine do it? Let's totally shift gears and look at artificial intelligence. At the very heart of modern AI, like those massive language models we're all using today, is an architecture called the transformer. You can think of the transformer as a neural network component that is entirely dedicated to learning incredibly useful representations of sequences of data. But here's the thing. An AI cannot just sit down and read a book or look at a painting the way you and I do. It needs that data chunked down into what we call tokens. Whether it's a word in a paragraph or a tiny, isolated piece of an image, a token is basically the fundamental grammar of AI. It's a unique mathematical vector of features that represents a single, solitary piece of data in a sequence. Under the hood, this requires some serious heavy lifting. The AI takes all those individual tokens, which are represented mathematically as n columns, and it collects them into a massive matrix with D features. This N by D matrix is the raw material. It's how the machine essentially maps its knowledge before it even starts processing. It creates the structured foundation for literally everything that comes next. And this isn't just for text either. In the realm of computer vision, a complex visual world, let's say an image of a tall building, is physically split into n square patches. Each of these patches is then mathematically reshaped and encoded into those feature vectors we were just talking about. So the AI is taking a complex, continuous visual world and chunking it down into a sequence of discrete mathematical tokens that it can actually read and process. Now, once the data is chunked into tokens, how on earth does the AI understand the context? It does this through a pretty genius mechanism called self-attention. This allows the model to figure out which parts of a sequence matter most to each other. It uses these asymmetric mathematical operations known as queries and keys. Essentially, the model is constantly asking itself, okay, based on this specific token right here, which other tokens in this sequence should I pay the most attention to? That's how the AI connects the dots and builds the big picture. This brings us to a really crucial point, because the parallel here between humans and machines is just wild. In human learning, using that Feynman technique, we actively try to identify and fill our knowledge gaps so we don't misunderstand things. Well, in AI engineering, developers do the exact same thing. They meticulously measure and mitigate risks to ensure the AI behaves safely and doesn't just confidently output a bunch of nonsense. A really perfect example of this is highlighted in Microsoft's 2025 Responsible AI Transparency Report. When we were developing their highly capable 5 family of small language models, they used what they call a break-fix framework. It's a cyclical, highly iterative process. They literally push the model, find exactly where its logic breaks or where it fails benchmarks, and then they go in and fix it. It is quite literally the machine learning equivalent of the Feynman technique's review and refine step. And one of the most fascinating ways they fix these models in real time is through something called groundedness detection. You know how sometimes AI models hallucinate? They just confidently make things up? Kind of like that one friend who pretends they read a book they absolutely haven't. To fix this, the system connects the AI to verified grounding documents. If the AI generates a sentence that isn't supported by that source material, the system immediately detects it and either removes the ungrounded output or rewrites it on the fly. It forces the AI to stick to the actual facts. Okay, so we've looked at the abstract math and we've looked at text processing. But what happens if we take these predictive models and actually put them inside a physical, moving, robotic body? What happens when artificial cognition is forced to physically interact with the messy, completely unpredictable real world, just like a human toddler does? To answer that, we turn to the absolute frontier of cognitive science and the incredible work of researcher Jun Tani. Tani built this fascinating robot that operates by integrating 2 very different things. First, you have bottom-up sensory motor data. That's the raw physics of bumping into things in the environment. Second, you have top-down abstract predictive modeling, which is the robot's internal expectation of what should happen. So the robot is constantly trying to match its mental predictions with its physical reality. And this setup leads us to a truly provocative question, one that really brings us to the climax of our explainer today. If a machine is constantly comparing its internal predictions against the chaotic outside world, is it possible for that machine to actually develop a sense of self? Well, the answer from Tani's experiments comes with a massive twist. In these dynamic robotic systems, everything runs totally on autopilot when the top-down predictions perfectly match the bottom-up reality. But when there's a conflict, when the robot completely fails to cope with its environment, an arbitration process kicks in. The robot is suddenly forced to take its own internal state into account. According to this model, the robotic self literally only emerges during these unsteady moments of failure and conflict. The self is a momentary phenomenon born entirely out of wrestling with the unexpected. Think about how incredibly profound that is. For us humans, true understanding emerges when we confront our knowledge gaps and wrestle with complexity, just like we saw with the Feynman technique. And for these advanced machines, their closest equivalent to self-awareness only sparks to life when they fail to cope with the unknown. It leaves us with a lingering, truly vital question to chew on. As we continue to bridge the gap between human learning and artificial cognition, what are we really building here? Thank you so much for exploring this with me today.